So we've got a subspace problem where we know that U and W are subspaces of V, and we want to show that their intersection must also be a subspace. And so by definition, what an intersection is all of the elements that are contained in both U and W. So first of all, we'll check our first property that 0 is in the intersection. And this must be true because U and W are subspaces. We must have that 0 is in U and 0 is in W because they're subspaces. And so because it's in both, 0 is also in that intersection by definition. So this one's good. And the second property, we want to show that it's closed under addition, so that if U and V are in U intersect W, then U plus V is also in U intercept W. And so, okay, so if we start with this idea that if U and V are in the intersection, then by definition, we must have that they're both in both U and W. And that V is in U and V is in W. And since U and V are both in U, this means that U plus V is in U. And if U and V are both in W, this means that U plus V are both in W. And so since U plus V is in both of them, this does tell us that by definition of the intersection, U plus V is in the intersection. So we've got that one. And then finally, we want to show the last property, right? So I'm just gonna make sure we underline the properties separate from the proofs. And the last one, we want to show that if U is in the intersection, then CU is also in the intersection for any real C. So we want to establish this property. It's closed under scalar multiplication. But again, if U is in there, same as before, we must have that U is in U and U is in W, and that's just the definition of that intersection. And in both cases, because U and W are subspaces, that means that CU is in U and CU is in W, and therefore, by definition, it's in the intersection because it's in both. So the intersection is a subspace.